Thank you for joining and thank you for your patience. So now we'll start with the session. So I welcome you all. We're going to the dynamic hackathon webinar series. And for today's webinar, uh, design critical systems and sensor integration and real-time software by our esteemed mentor Bharat Shivaji Kokate sir. So as you guys know, like technology is rapidly evolving and designing critical systems has become more essential than ever. So these systems are vital in the industries such as automotive, aerospace, healthcare, industrial automation, and so as in now in crane industries, where reliability and precision are crucial to prevent failures and ensuring safety. So today we are fortunate to have an industry expert with us who will guide us through this important topic. Before we begin, some quick points to remember. Like we will have a detailed session by our esteemed speaker, followed by an Q&A session. And please feel free to drop your questions in the chat. And please ensure that your mute, mics are on mute during the session. At the end of the session, there we will have an interactive Q&A session. Now I'm honored to introduce our today's esteemed speaker, Mr. Bharat Shivaji Kokate sir. He's head of embedded systems at Aeron Systems Private Limited. So, so he is an embedded system expert with extensive experience in design and implementing real-time safety critical applications. As the head of embedded system at Aeron Systems, he's been playing a pivotal role in developing advanced sensor-based applications and driving cutting-edge innovations in the embedded technology. With a deep understanding of safety critical architecture, sensor fusion, and real-time software optimization, is passionate about mentoring the next generation of innovators and students. Thank you, Bharat sir, for joining us today, and we are excited to learn from you. Now, it's over to you.
Thank you, Saurabh. I'll just share my screen first. I hope the screen is visible now.
Yes.
Okay, so good evening, everyone. Once again, thank you all for joining. Today's session will be mostly about designing the safety critical systems, and we'll discuss more in detail about integration of various sensors and developing of real-time embedded software for such applications. And we'll take the questions at the end. You can either write them in the chat box or keep them ready, keep them handy. I'll start with my brief introduction, although Saurabh has introduced me, but I'll just once again brief who I am and what I'm doing at Aeron. So I have been at Aeron for the past about 13 years and presently holding the position of head of embedded systems. For a brief time, I was in the telecom sector in the transmission department for about 3 years. I've been part of various hackathons and I have been there in different roles, but I was never there as a participant. So you all guys, you are very much passionate and very much. I know that you are going to be good at whatever hackathon you are going to participate at right now. This will be my ninth hackathon, and I'm ready to help you with any queries if you have. I'll be sharing my LinkedIn profile at the end of the session. So whatever, I'll be very much happy to help you out. So with this, let's begin with the first topic of today's session. The session will be divided in two sections. The first section will mostly talk about various sensors and integration of sensors. And the second part is about the real-time systems, which is again very much linked to the first session. And this first part is going to start with the first topic will be sensor selection. There are few things that you are supposed to keep in mind when it comes to selection of sensors, and that starts with the requirement. whenever there is a problem statement, it only defines, or rather it is only supposed to define what the sensor should do and not the technology that the sensor should be at. So, for example, they can say that you are supposed to detect an obstacle, but ideally, a requirement should not say that the obstacle should only be detected by either using a LiDAR or a LiDAR sensor. Again, this example will be very much throughout the session. I'll be taking this example because it is very much easy to correlate. Ideally, whenever I say that the requirement should not specify the technology, but at times it is a condition that this technology itself is defined in the requirement itself. So you are supposed to take care of the requirements when it comes to sensor selection. Next, the second criteria would be we should be selecting the sensor not only based on requirements but also based on the safety standards. Now, what does that mean? If you know that this particular hackathon is going to be for either cranes or safety critical applications, very much similar to cranes. These applications are usually required to sustain or specify the criteria that are required for safety of that particular application. So you are supposed to take care of those safety standards and decide what the sensor, whatever sensor you are supposed to, or rather you're selecting is meeting those safety standards. These standards vary depending on the industry that you're going to use for. For airborne industry or for military standards, the safety standards are different, and for cranes and other applications, the safety standards are different. These need to be very much taken care of when you select the sensor. Next, coming to the performance, it may happen that you have selected the right sensor, the standards are also meeting, but the sensor is not able to perform as per the requirements. So whatever accuracy related things or whatever voltage requirements, analog sensor requirements, whatever is related to that particular sensor, you are supposed to take care of the performance when it comes to those kind of requirements. Next is, this is again very much related to the second point, that is safety. Since we are talking about critical applications, there might be a necessity of having a redundant sensor, or you are supposed to have any kind of fail-safe mechanism for the sensor that you are using. For example, if there is a requirement of having LiDAR for obstacle detection, it might happen that since it is going to be used in a very much safety critical application, what if your LiDAR fails? Do you have a backup plan for that? So that needs to be taken care of. It may or may not be mentioned in the requirement in the problem statement, but this will be a plus point or a additional mechanism and a feature that you will have in your solution, which will help you have redundancy and have a very much minimum risk of failure when it comes to the sensor failure itself. At times, it is very much not possible to have two sensors. What if the one sensor itself is so out of budget that the whole solution is not going to be, or it will not be feasible to have two sensors of the same kind. In such cases, it is desirable to have a mechanism to either diagnose the failure or indicate that the failure has happened. Again, coming to the same example, what if the LiDAR fails? And what if you just indicate to the operator of that particular vehicle or that crane that there is some kind of failure in the sensor, or there is some kind of failure? The operator is supposed to take action based on what kind of failure it is. You can indicate the failure in terms of 2-3 stages. It might be a warning or it might be a failure itself. So you indicate something somehow so that the operator will act upon based on what kind of failure it is. So diagnostics of the failure of the sensor should be taken care of. Now, suppose everything is in place, you have decided what sensor you are going to use, it is meeting the safety standards, the performance is in line what is required. But what about this environmental safety of that sensor? If it is a LiDAR sensor, it is supposed to be outside of the vehicle. It is supposed to be somewhere where it is looking at the environment which is outside of the vehicle. So you are either supposed to cover the sensor in such a way that it is safe from dust and moisture and other environmental conditions, or you select a sensor which has inbuilt capabilities of saving the sensor from the environmental safety. This is also linked to the last point, that is ingress protection. So there are IP ratings, IP65, IP45, 43, 33. The combination of these two values defines either the sensor is uh, safe from dust or safe from water. So you are supposed to, if this is not mentioned in the requirement, you are supposed to get it clarified. Or if this is, there might be assumption that you can have for yourself depending on where the sensor is going to be installed. You yourself can understand that either if the sensor is inside the cabin where the operator is sitting, you need not have much safety to that equipment because it is very much safe from dust and water in that case. But if it is outside of the vehicle, all of these points are supposed to be considered. Next thing is about identification of what the sensor is supposed to do. This is the first step actually that you should be taking care of. Uh, for example, if you are supposed to ask, if you are asked to identify the position of the vehicle, it is obvious that you are supposed to have a GPS receiver inside your device, right? Next, if in the same use case, they are asking you to send this particular location of the vehicle to some remote server. So again, it is obvious that either you have a 4G modem or a 5G module in your device so that you can connect to some remote server and send the data to the remote server. So you actually understand what the functionality of the sensor and the system is supposed to be. Uh, Again, coming back to the obstacle example, for a single use case, that is identification of obstacle, you have multiple options. You have radar, lidar, ultrasonic sensor, or proximity sensor. So you, based on what exactly is the use case, if the problem statement can be solved using 4 sensor, you're supposed to compare, understand, and then decide what is the best sensor for your particular use case. This can be done using multiple categories. One of them is cost. Second is the distance that you have to measure. The distance of proximity sensor might be very much lesser, but maybe the accuracy is high, maybe. LiDAR will have higher ranges, ultrasonic will have higher ranges, but the usage of LiDAR and ultrasonic will be different. If there is obstacle that is of a transparent nature, maybe glass, you cannot use a LiDAR sensor. Either you use ultrasonic sensor or something else, but LiDAR cannot be used. So depending on what the use case is, you are supposed to decide the sensor. Uh, Again, comparison is necessary because you have lots of options that are available in the open market. You are supposed to explore, understand the pros and cons of each of the sensor, and then prepare a checklist for yourself. Depending on the criteria that I mentioned before, cost will be one example. Is it going to be usable in this use case is another example. Maybe the failure conditions and the redundancy conditions can be taken care of in the same checklist. So you have a checklist, and wherever you have the maximum number of ticks, that is your sensor that you are supposed to select. Another important thing is, which might not be possible in case of hackathons, but you are supposed to evaluate the sensor first. What does that mean? Suppose you have 3 options. All 3 options are almost filling up the criteria. You have tick marks, 5, 6 tick marks for each of the sensor. You are supposed to get a evaluation board of that sensor or the sensor itself, prepare a prototype only for that sensor, and thus test those 3 sensors and then compare them. Since again we are talking about a hackathon, if it is not possible and if the 3 sensors are of low cost and can be afforded, you can get all the 3 sensors and during runtime you evaluate them and then decide which is best out of them. Uh, One more option is to see what the in the open domain you might have information for all the other use cases which are very much similar to your problem statement. So see what those people are preferring to and what are their take on the sensor that they are using. So you get a fair idea on how the sensor can be utilized, where it is to be installed, and how it is to be used. Again, since we are talking about safety critical applications, the standards become very much necessary. We briefly talked about them a while back, but a common mistake, and it is not deliberate, but most of the people make is during the prototype phase, they don't take into consideration the safety standards and most of the aspects that are mentioned here. So even if the prototype meets all the performance standards or the safety standards, because something is missed, most of the applications or the solutions that they build never go into production. And this is also one of the problems or one of the major mistake that many of the small startups make. So you focus on the prototype. In the prototype phase itself, you focus on all of these so that you make use of the best sensor, the best solution comes out of it, and then it is definitely readily usable just after the prototype phase itself. Again, even if you're using readily available sensors and the development boards, it might be possible that some tweaks can make those sensor itself into a safety usable sensor. So again, taking the same example, if you get a sensor which is not IP rated, and what if you make an enclosure for that sensor such that you make the sensor protected from dust and water, so your sensor now becomes a usable sensor. So don't rely on what is readily available. Think out of the box and make sure that you do something to make it fit into your requirements. Uh, See, prototyping phase is the first phase that you will be doing. In hackathons also, we are building prototypes. We are not building the final product. But the uh, thing that we don't take care of is making the solution usable. So I've been part of hackathons and I've seen people build solution. Everything is on the table, but it is not a usable solution. It is not an integrated solution. So looking at all these features that we have mentioned, I'll talk about MTBF. We missed MTBF, but looking at all the requirements, all the feature performances, you see that you build an integrated device, something that goes inside a box, something that is usable. Maybe you will have to have two boxes connected to each other via wires or cables, but try to build. You have 3D printers available nowadays. It was not available earlier. So try to enclose everything so that everything is not placed up just on the table. Instead of trying to make a working solution, trying to build a usable solution. I'll talk about MTBF briefly. Uh, See, one of the requirements that every problem statement is supposed to have, what is the time before the solution fails? So again, since we are talking about safety critical applications, what if the solution that you have built is having a mean time before failure of just 10 hours? What does that mean? The time you install the solution on the platform, and what if after 10 hours, since your MTBF is just about 10 hours, what if it stops working after 10 hours? So ideally, depending on where it is installed, the MTBF should be as high as possible, 20,000 hours, 20, 50, whatever it is, but it should be high. And it should be mentioned so that the operator and the crane manufacturer and the crane service engineer knows that this is when the device is supposed to come back, get serviced, and goes back so that the MTBF increases again. This is just like servicing any bike or motor vehicle that you have. Okay. See, no matter what, there is always a chance that the system fails. It might be because of internal power failure or a faulty sensor or some component that goes faulty. So it is definitely possible that the system fails. But depending on the risk analysis or the risk assessment, the failures are supposed to be categorized depending on what application it is, either into minor, major, or hazardous or catastrophic. Uh, See, if it is a solution that is only supposed to send the position of the vehicle to a remote server, it might be considered as a minor category failure if it fails at all. Because again, it depends on what the vehicle tracker is being used for. If it is used for vehicle tracking, that means it is a critical application, because what if the vehicle is stolen, then that becomes a critical thing. But what if it is only to decide where the crane is installed right now? So probably whenever it was installed for the first time and you have the data for that, and then it fails, then it is okay to know the last known location of that crane, because it is not easy to move a crane, right? But if it is a obstacle detection system, it either goes into hazardous or catastrophic condition. If the solution fails and if there is an obstacle at all, it will dash to that obstacle and it will cause loss of either human life or maybe some other maybe a nearby building or something like that. So depending on where it is installed, what is the use case, the risk assessment and the failure of that particular system is supposed to be taken care of. Uh, it might happen that the failure is not causing any kind of there is not no fact as in nobody dies, but what if there are serious injuries, then it can be considered either hazardous in that condition or a major failure also. So likewise you can define the category for your failure systems. uh, Another basic example would be what if your horn of your two-wheeler fails, it is very much minor or no failure at all condition. Okay. So based on the risk, you are supposed to do a assessment. Now this is where the fail-safe mechanism comes into picture. You either install a redundant sensor, or have a redundant power supply, or have a redundant system in itself. So what if you have two obstacle detection systems, totally independent? The power supply is independent, the sensors are independent. So you have a system level redundancy in these cases. Okay, these are some of the common sensors that are usually used in crane industries. We have load sensors, encoders, limit switches, and the lidar and lidar for obstacle detection. Wind sensor, also known as anemometer, to detect wind speed, based on which the operator can either decide to operate in those windy conditions or stop if the wind is too high. And temperature sensors for overheat detection. Again, based on the problem statement, you can use any of these sensors. Again, this is a very basic list. There are many more sensors and you can select the sensor depending on the problem statement. Uh, some of the other sensors could be ultrasonic sensor or vibration sensor, maybe accelerometers for shock detection, or GPS and proximity sensors also. Okay. Now, again, this is a very important parameter during sensor selection. I have seen people misunderstand or rather not take care of these interfaces and then build a solution and later on say that अरे ये तो नहीं चल रहा है. So for example, uh, if the system is modular, your controller and all the systems are sitting inside the cabinet where the operator is sitting, but your lidar sensor is supposed to be outside of the cabin. In such an application, you cannot use interfaces which are not meant for long distance communication. In a example like crane, the distance might be from starting from few meters to maybe 10 or 20 meters, depending on what is the length of the sensor, where is the obstacle supposed to be detected. So in such systems, you are supposed to use either 422 or Ethernet or something that is meant for long distance communication. If the distance is short in few meters, you can use RS232. But what people do is they select LiDAR, which either has SP or I2C, and when they increase the length of the cable, the sensor does not work. So maybe you'll have to have an additional controller which is sitting near the sensor itself and have a main controller which is inside the cabin. So again, depending on the use case, you are supposed to decide what interface you are using for your particular sensor. I don't know if you all are aware about these, but most of the interfaces that are written here, Ethernet CAN, these are supposed to be used for long distance. 422 also for long distance communication. SP and I2C for very short distance communication, maybe on board or just next to your device. And analog sensors again for very short distance. You cannot have long distance analog sensors. UART for short distance again. Okay, one of the most ignored parameters while selecting sensors, and one of the most critical parameters when it comes to uh, safety critical sensor selection. See what happens is if a sensor is supposed to detect something, it is supposed to be sampled based on what it is supposed to detect. Giving you an example, again, if it is supposed to detect an obstacle, what if the sensor is sampled so slow that it will miss the obstacle when you are moving at a certain speed or more than that? So we'll take a few examples for that. See, since we are talking about safety critical systems, the sensors are supposed to be sampled at an optimal speed, not very high, not very low. So it does not make sense if you are sampling an obstacle detection sensor every second. You will definitely miss an obstacle if the you pass the second and you already dash that particular obstacle, right? On the other hand, some of the sensor can deliberately be sampled at a very low speed. For example, your fuel level monitoring sensor, maybe an ultrasonic sensor, it can be sampled at very low speed, maybe once in a minute or maybe every 10 seconds. Can be very slow, right? Your even if you miss a sample, there is no harm in that. Your fuel is not supposed to go at that rate low, and even if it goes, it is not going to cause any problem as such. It is just for monitoring purposes. But sensors which are really going to cause harm are supposed to be sampled at a higher speed. Uh, so depending on the use case, please select the right sampling frequency. Also, you are supposed to take care of multi-sensor sampling. What if there is a dependency on two sensors, as in one sensor has some kind of dependency on two sensors? Again, we'll take an example. Suppose we have two LiDAR sensors, both are being used for the same use case. What if you sample one sensor at 100 Hertz and other sensor at 10 Hertz? Now, since these two sensors will not be at sync, you cannot ideally use them as redundant sensors because they are not in sync. They are supposed to give the same information at the same point of time whenever you're sampling them. So you see that the same kind of sensors, when either they are being considered as a redundant sensor or as a backup sensor, you sample them at the same time. Next, if you have multiple sensors, not for the same use case, you can decide the sampling rate which is independent of each other, and it is exactly vice versa of the previous example. It is supposed to be dependent on what the sensor is doing in the second use case. Multiple sensors, not for the same use case. So have the sampling frequency based on that particular sensor. Now, what if the sensors are capable of sampling at very high speed, but you and the whole system is out of time to sample the sensor? See, sensor sampling is not the only thing that the system is supposed to do, right? It is supposed to use that data to do something. So what if the entire duration that you have is not capable, or the system is not having sufficient time to respond to everything that it is supposed to do? In such conditions, you will have to alter the sampling speed, but still have the optimal speed based on the availability of the time that you have. As a system as a whole that the system has, you are supposed to select the sampling time. Finally, it also comes down to the sensor capability. Even if the sensor that you have selected has, as in you have sufficient time to sample the sensor, you have decided the time that you have, but some system, the sensor itself should be capable of giving data at that particular rate. Again, for example, if in case of I2C, you will have to query and then you get a response. So this time that you have for query response is going to be lesser in uh, uh, in applications where it is possible that the sensor itself is giving the data output. So if suppose the sensor has UART interface, it can send data by itself. So you need not query. So the time required for query response will be higher than the time required wherein the sensor is giving the data by itself. This is something that is in line with the previous thing that we talked about, but it is going to be critical when it comes to giving the actual output. I'll tell you what. Suppose you are using analog sensors and they mostly are going to give you very noisy data. The data that is the raw data will not be usable always. You will have to have some kind of filtering or some kind of either hardware or software, some kind of filtering that is going to give you something that is usable. So in order to do that, you will have to have filters that are running either on software or hardware so that you remove the noise, the biases, the offset, the random errors that you have, unwanted spikes, or maybe unwanted frequency, everything that is to be removed from the data. And then you get the usable data. Now, in order to do this, in order to remove the unwanted signals, you will have to have filters which are going to take time, right? It is a software filter. It will take some time. So when we talked about the previous thing, sampling of the sensors, you are also supposed to take care of filtering of the sensors. Again, uh, maybe you there are so many filters that you can be applied, but the system as a whole should have a capability of running that filter on your hardware. See, I assume that when we are talking about safety critical application, it is possible that we are talking about embedded systems which are not having operating system running on them, and they are very slow speed devices, maybe running at few megahertz, 200, 400 megahertz, not more than that. In such cases, the system, when it runs a critical filter, which is a complex filter, it will take some time to run, maybe a second, half a second, depending on how critical or complex the function is. So your system is supposed to be capable of running the filter that you have decided to use. So see that you apply optimal filter, and it might happen that your sensor is capable of giving you data 100 times a second, but your filter itself is taking more than a second to run. So the sensor sampling is of no use. Okay, so execution time of that filter is supposed to be taken care of. Next is the bandwidth of the system. Uh, see, uh, if it is a GPS, it is very slow sampled, maybe once in a second or 10 times a second, not more than that. But in case of, if suppose you are detecting shock, you have to have your bandwidth above the shock detecting capability. You all must be knowing about Nyquist criteria, that is talking about sampling at least twice the frequency. So decide the sampling frequency also based on what the bandwidth you are using and also based on what the filter you are using. Your filter is not supposed to cut off the sensor bandwidth at the wrong bandwidth, right? If you cut off at maybe 10 hertz or lesser than that, you will lose the data that you are actually supposed to be utilizing. So select the right bandwidth and also select the right filter. There are in open domain, you will have lot many filters available. Uh, the filters can be chosen based on various criteria, but you see that the filter that you are selecting, either hardware or software, are fitting the timing and the bandwidth criteria that you have decided for your system. Okay. Again, very ignored parameter, very important. Calibration of the sensor is ignored just because at times you don't have a reference for that sensor or the system. So that does not mean that you're not supposed to calibrate the sensor, but at least you can at least verify that the sensor is working right. For example, if we had have a lidar sensor for detecting the distance, you can easily verify that the lidar is working fine. What you do is you mark multiple steps uh, on the table: 1 centimeter, 10 centimeter, 50 centimeter, 200 centimeter. Keep the lidar at 0 point, and then just keep something that is creating an obstacle, and then measure that the sensor is giving the right output. At least this can be done to verify that the sensor is working fine. For a temperature sensor, maybe you can have another calibrated temperature sensor just as a reference and see that the temperature is fine. So wherever possible, see that you are at least verifying the output of that sensor, if not calibrating the sensor. But when it comes to calibration, it is possible. These are some of the options that are uh, available when it comes to calibration. The first one is bias or offset removal. We'll take an example of the lidar again. Suppose your lidar is giving 5 meter instead of 3 meters, 10 meter instead of 12 meters, and 20 instead of 22. So you always have a constant offset of 2 meters. So you are just supposed to add 2 meters to whatever reading that lidar sensor is giving. So that is a offset type of error or a bias type of error. The other example is again same example. Instead of 5 meters, your lidar is giving 2.5. Instead of 10, it is giving 5. And instead of 20, it is giving 10. That means it is giving half the value always. So that means there is a scale factor error of 2. So what you are supposed to do is you are supposed to multiply whatever output you are getting by 2. So you will get 20 when you are giving 10 meter. There is a very high possibility that the sensor is having both the errors, scaling as well as offset error. In such a case, you can remove both of them. It is very much easy. You can find out what the output is, and then you can uh, plot it and then define the scale factor error and the offset error and just remove it as a formula. Uh, Non-linearity error, somewhat difficult to find out, but can be done. Again, in the same use case, what is happening is the scale factor is changing over time. So suppose the scale factor below 10 meters is of 2, 10 to 28 is maybe 1.5 or 3, and 20 to 30, the scale factor is 1. That is, there is no error. So the scale factor itself is changing throughout the scale. So you are supposed to fit it depending on what the value is, what the raw value is. So this is something that is non-linearity kind of error. Uh, it is also a possibility that the error itself is non-linear, which is a bit more difficult to find out, but can be done. Also remember that the scale factor error can also be negative. So you can also have scale factor as -2. Uh, the next problem or the next error usually that comes up is temperature dependency. This is not common in digital sensors, but in analog sensors or the ADC itself are at times temperature dependent. So suppose you are giving the same value. Suppose you have a analog lidar. You are giving 5 meter as an you are calculating the distance of 5 meters, but due to the environmental conditions, the temperature is changing. So early in the morning, when the same lidar sensor was detecting 5 meters, maybe by afternoon or evening, when the temperature is rising, instead of 5 meters, it can say that it is 3 meters. So you are supposed to calibrate the sensor and the whole circuitry for temperature dependency also. Uh, Lastly, some of the sensors, they require some special tools and equipments for calibration. For example, accelerometer calibration is very difficult, or pressure sensor calibration is difficult. So, or even anemometer calibration is difficult. How do you measure the wind speed, right? You don't have a if you don't have a reference sensor, you cannot verify that the anemometer is working fine. So, in cases like hackathons, you can assume that the sensor is calibrated for such sensors, wherein it is you need some special kind of equipments and setup to calibrate or verify those sensors. we can just assume that they are calibrated and then use them. But you can still definitely try for some kind of basic calibration for all the other sensors. Okay. With this, we are ending our first session, that was sensors. If you want, we can have a very short break of maybe 1 or 2 minutes just to write your queries down for the sensor, and then we start with the second session.
Yeah, we can have 2 minutes break.
Okay. So now that the sensors are in place, you see, we are talking about safety critical systems. It is safety critical because it is supposed to respond to an event as soon as possible. Uh, so even a delay of few milliseconds can make a huge difference. We'll take an example. Suppose a autonomous vehicle that is moving at only 35 kilometers per hour. And what if it detects an obstacle and the time to initiate the braking of the system gets delayed by 100 milliseconds? The vehicle will move about 1 meters if it is delayed by 100 milliseconds. So there is a very high possibility that it will hit the obstacle or the person or whoever is standing in front of the vehicle. So even a delay of 100 milliseconds at 35 kilometer per hour, if it is making a huge difference, you can assume that in applications like crane, if you're detecting obstacles, you are supposed to sample the sensor more than 100 milliseconds of speed, right? Maybe at 1000 samples per second. Okay. So the overall delay of the system has to be right, and the sensor sampling to the action that is being taken, the delay should be, or the latency should be very much low as possible. So let's see how this can be achieved. Uh, See, most of the things are going to be relatable to the previous session. It is, we'll have to briefly see some of the points that we have discussed once again. In order to get fast response or low latency, these are some of the points that are supposed to be taken care of. First is defining the end-to-end data flow, right from sensor sampling to the output that is going to be happening. You're supposed to define a flow of the events that are going to happen. So you actually draw a flow chart mentioning from the power on of the system what are going to be the sequence of events that are going to happen, at what uh, frequency are you sampling the sensor, when is the action taken care of, if there is no action, what is the thing that you are going to do, or is the system going to sit idle? So you define the flow of the system completely, make a flow chart, make a flow diagram, and then you define the uh, functions that the system is going to do for the software. Uh, Again, since we are talking about sensor sampling, the sensors are not going to give you the actual output. They are going to give you raw counts, or maybe LiDAR will give you in terms of meters or something like that. But many of the analog sensors, they are going to give you raw counts. The temperature sensor will not tell you that it is XYZ degrees per centigrade. It will tell you counts. It will tell you 10,000, 2,000, depending on the resolution of the sensor. So you are supposed to take care of conversion of the sensor raw value to the actual value in the flowchart itself. People, what they do is they just start coding when the problem statement is defined. That is not how you're supposed to work. You define the flow first and then start coding. That will be a lot more easier than the first way. Next, once the flow is defined, you are also defining the sampling speed depending on what we had decided earlier, the use case and everything. And then you take care of how you are supposed to, or the system as a whole is supposed to going to control the bandwidth. Uh, uh, See what usually happens is, even if you are sampling the sensor at very high speed, the filter will cut off the data so that the bandwidth becomes so low that it becomes unusable. Uh, Again, talking about analog sensors, if you have a RC filter for a temperature sensor, again, temperature sensor is not a critical application, but it is easy to define for this example. If the temperature is increasing every 10 degree per second, example, if your the hardware filter is so low that it is going to give you very slow response, maybe the actual output of the filtered value is going to be 1 degree per second. So that is not desirable, right? Your sensor is capable of giving a temperature change of 10 degree centigrade per second, but you are having the wrong filter, which is giving you the wrong bandwidth output, as in non-desirable output, and then that becomes very slow, non-usable data. So see that the bandwidth is being controlled and cut off at the right thing. So brainstorm, you have multiple people in your team, everybody sit together and then decide what the flow is so that you select the right frequency and the right bandwidth. This gives you clarity in the beginning itself. So you start building the right solution from the beginning itself. Uh, See, sampling twice the output data rate is again a desired value, but there is no harm in having a very high sampling rate. If your sensor and the system is capable of, try to have it at 4 times or 5 times the output data rate so that you can have a better filter control and maybe get a better output also. Uh, in a system, your filtering, this again we have talked about, it is not only about the digital domain, that is the software domain. You also have to have the right filters in the analog domain, the way I explained in the temperature example. So do not damp the output, but also see that you are not losing the important information out of the sensor. Sensor fusion, when you are using two sensors for the same use case, see that you are sampling them and combining the data uh, in the right format. So suppose you have two anemometers, either they are for redundancy or better accuracy. There are various ways of using those two sensors together, right? For example, even if they are for redundancy, what if you use both the sensors, average them out, and then use the output? And then if any of them fails, you rely on the other sensor that is working. So it is your choice or your decision to use the sensor in the right way. Uh, Apart from average, you can also have, suppose you have two anemometers. One is a low cost sensor, which is going to act as a backup sensor, and one is a very high quality, high speed sensor. In such an use case, you can give more weightage to the high quality sensor and lesser weightage to the second sensor, and then you make use of the output. But the easiest is always taking an average of both the sensors. Uh, this is related to the examples that we talked about earlier, the 100 millisecond example. So a delay of 100 millisecond, if it is causing 1 meter of an error, uh, this is because the sensor was able to detect the obstacle well within time, but the delay of the system was of 100 milliseconds. The overall delay of the system was more than the desired value. Another possibility is the sensor itself is either sampled at the wrong frequency. That is sampled, for example, it is sampled every 100 millisecond. So the sensor itself is giving you data at a very slow rate, which makes it unusable. So in any case, the latency is supposed to be calculated and then defined as per the use case, so that the time constraints and the latency and the time to act, depending on where it is supposed to be used, everything is in sync. Taking an example of a crane, suppose the crane is rotating and at an maximum rate of suppose 10 degree per second example. So if you know the distance between the arm of the crane and the obstacle, you can easily calculate the time that the crane will hit that obstacle. It is easy to, you know, the length of the arm, you know, the rotation rate. You can find the distance between the obstacle and the crane when it is moving at XYZ rate. And then you decide that I have a few milliseconds or few seconds, and that becomes your desired maximum latency of the system. And then you fit in everything inside the time constraints that you have now. And then the system becomes a low latency and a usable system. Okay. See, everything that we are talking about might seem repetitive, but these are interlinked terms, and all the terms are very much important for real-time systems to work. Even if we know that the timing constraints and the desired latency, at times the things are not in our control. For example, if the overall latency of the system should be less than 100 milliseconds, what if the sensor itself takes 50 milliseconds to respond? So you are left with just 50 milliseconds for rest of the work to be completed. So 50 seconds are taken by the sensor, which we cannot do anything about. But the other 50 seconds that are left out are supposed to be utilized for applying calibration coefficients, using the right filter or applying the right filter, and then taking action. Again, even if the system is doing everything in those 100 milliseconds, the thing that is being controlled may not respond within that certain time. For example, if you're asking the crane to stop movement because you have detected an obstacle, but if this the arm of that crane, if it is going to take a few more milliseconds or a few more seconds to respond, if the motor is still rotating and then the speed gradually decreases and then it travels some more distance, and it will eventually hit the obstacle, right? So either you choose a sensor which is of a longer length so that you detect that there is something earlier in the system, or you decrease your system's overall delay time, or you have a cutoff for the motor or the actuator such that it cuts off when you say that it's time to cut off. It is not always about taking action. Sometimes you are just supposed to run an alarm or indicate using some light. In that case, it is an instantaneous thing wherein the operator is supposed to take action and you are not controlling the system directly. So this too, as in the operator too, will take some time to react. That also is supposed to be considered. Uh, so timing analysis for each stage is very much necessary, and the addition of that all the timings becomes the latency of your timing, and that is the time constraint that you're going to have. Okay, a bare metal system. I hope that you know what a bare metal system is. It is a system that is not having an operating system, something that is firmware based. So usually most of the embedded systems are supposed to run bare metal codes, but since the availability of very much light operating systems and high speed processors, nowadays embedded systems also have operating system and processors as well. But the problem with operating system based systems is the overall response time and the time taken by the operating system itself is not in our control. So the time to service interrupts, the time to control digital outputs, and the time to use onboard peripherals like SP and I2C for operating system based systems is very much high. And since it is in the control of the operating system, you cannot tweak it after some point of time. So if you are supposed to use a maybe a digital output, suppose the GPIO based interrupt, bare metal system will be much more preferable than having operating based system because they are much more efficient when it comes to interrupt handling. But again, uh, one more thing, the one more problem in operating based system is the time to boot. What if your system restarts when it is in use? Again, taking the same example, what if there is an obstacle? It was supposed to detect an obstacle and the system restart. The operating system itself will take few seconds, minutes to boot. But in terms of embedded systems, it is very, very less. Or you can have a system configured in such a way that the boot time delay is just a few milliseconds. So it is very much desirable to have bare metal systems for operating systems, but that is not always an option. You can decide based on the usage of the system, based on the use case. Okay. Again, suppose it is about just sending the data to the remote server and it is about monitoring of the fuel or monitoring of some parameters of the vehicle. You can easily use operating based systems. The latency would not matter much. Even if it is few seconds, even if you need few maybe 10 seconds to send the data to the remote server, it is okay. So operating system based system is actually desirable in these systems because it has all the necessary uh, you can easily connect a 5G module. You can easily have FTP, HTTP, MQTT running on those systems, and then easily send data to those remote server. In such applications, bare metal system will actually create a problem. So depending on the use case, you select the right thing, that is either bare metal system or operating based system. For fault detection, obstacle detection, see that you are using bare metal. It is recommended to use bare metal. Okay. With this, we are ending the session because since this session is for a hackathon, I would like to give you some tips. I think that you will like this. First thing is always plan first. Decide what you are trying to achieve and brainstorm, sit with all the team members and plan everything first. Read the problem statement at least 10 times and understand the problem statement first. That is the thing that you are going to work on. And if you understand it incorrectly, you are going to build a very unusable and incorrect solution. Reach out to the organizers if you have any doubts. You reach out via email or whatever is preferable, and then get the right understanding regarding the problem statement. See that you are meeting all the primary requirements first. I've seen people build fancy items. They add on, they have very much fancy add-ons to the solution that they are building, but the solution is not having the primary requirements, and then they don't win. And then they say that कि हमने तो बहुत मस्त बनाया था पर हम जीते ही नहीं. See that you are looking at the primary requirements. It is supposed to do what it is supposed to do first, and then you have all the additional features that you are going to have. Even if you're in such cases, even if your solution is very good, it will not be usable. Involvement of all the team members is very much necessary. It is not a one man's task. It is not a one man's job. See that everyone is contributing. Everybody should give at least do something that is going to help the solution be on track and give out a best solution possible. Uh, with this, I would like to wish everybody who is participating a very best of luck, and I would like to see a very healthy competition. And thank you all for listening. And I'm open to questions if you have any.
Thank you, Bharat sir, for this insightful session. I hope everybody has learned about the basics of the sensors and their integration and the type of sensors and also the software optimization or development of software using the sensors. Yeah, we are open for the Q&A session right now. So if you have any questions, please put it in chat box. So you can like raise your hand and ask the question, or you can like unmute yourself and ask the question. No questions here. Okay, I have one question, sir. Like, so, so someone did raise the hand. Yeah, you can unmute yourself and like. Okay, I have one question. So many of the problem statements require to use LiDAR sensors. So LiDAR is quite expensive, and sometimes it's also quite hard to learn or to like integrate uh, for students. So what can be an alternative to that?
See, ultrasonic is also an optional sensor for to LiDAR. Ultrasonic are cheaper sensors. Nowadays, we are getting smaller ultrasonic sensor, which was not the case a few years back. Uh, but one of the reason why we go for LiDAR is the accuracy and the distance that the options that we have for distance in case of LiDAR sensors. See, cost is one of the very much critical factors because we are talking about students here. Uh, but there is no option right now. Radar is one of the options, but again, cost is a very much critical factor for radar as well.
Yeah. So we have one question. If we do research and come up with great idea, but have any organization support early stage ideas and will help funding and development. So Varun, I guess this question you already asked in our chat group. I guess Harshvardhan has the organizer team must have replied to you. So if your idea gets selected for the grand finale, they like, and it's quite good. If they like, do like your idea, they will think of like giving a funding to you. So basic idea of this hackathon is like there are solutions available. The problem statements are given, but there are quite solutions available. But the thing is that we want students to come with something innovative. Even if you don't use sensor or don't show any prototype or don't show any like MVP product, it's fine with us. But we want you to like see, learn about the already existing solutions and try to find something different, like or use something, like do something innovative in that. So that is main motto of this hackathon. Or you can also think of improvising the existing solution, making it cost effective. So first is you have to like understand the concept, understand what you can make, how you can make a difference in that already existing solution. This is all. So one question we have is how can we improve the reliability and longevity of the sensor, especially, especially in harsh and challenging environment. Harsh and
Right. Filippo, in cases wherein you are supposed to increase the reliability of the sensor, uh, there are two options. You select a sensor which is capable of sustaining such kind of harsh environments. So when we say harsh environments, again, there are categories of those conditions, maybe shock or a sudden acceleration, or another is when it comes to harsh, it might be very high dust or heavy rains or something like that. So you select a sensor which is made for such kind of applications, or you build something around the sensor so that you increase the life of the sensor and also make it sustainable for such kind of environments. The second thing is at times not possible and also not desirable, because no matter what you do external to the sensor, it is difficult to test those conditions. So simulation of harsh condition itself is going to be a very much difficult task for you. So suppose you make a sensor that is going to sustain, suppose 10G of shock. How do you verify that it is sustaining 10G of shock? So instead of that, what you do is you select a sensor in the data sheet where it mentions that it is supposed to sustain 10G of shock, and then at least you have something on paper wherein it is verified by either the sensor manufacturer or somebody else that it is supposed to sustain such kind of challenging environments. I hope I have answered your question. Uh, Amit, coming to your question, see, industrial sensors are dependent on what industry are we talking about. If it is an industry that is indoors, the sensors are going to be different than the other kind of sensors. Again, usually manufacturers of the sensor make the same model for various industries. So you can have the sensor for automotive industry as well as for commercial use also. So the sensor that we are using in our mobile phones, those are commercial sensors. But the similar or same sensors are ruggedized and made such that they are usable for automobile industry. So this is just an example, but you will have to specify what industry you're talking about. Uh, okay, Amit had sent the same question.
We have like, what are the trade-offs between accuracy, power consumption, and cost when designing a sensor for specific applications?
Uh, Again, depends. It need not be. It is not always the case wherein the accuracy is related to power consumption, but at times accuracy is definitely related to cost, or most of the times it is related to cost. Power consumption is not very much. Uh, Again, these three are actually not linked. Accuracy and cost is linked. Power consumption is not linked. Power consumption becomes a critical factor when your system is battery based. So suppose it is a drone. Now again, in cases of drone, it is supposed to travel on a standalone battery backup and also use that battery backup for sensor. Suppose in such a case, power consumption becomes a critical factor. But in cases like cranes or in automobile, you have power that is being coming out from the system. It is everything is getting powered on from the battery that is on board, and that is also getting recharged while the vehicle is running. So in such a use case, power consumption really does not matter. Again, I hope I have clearly answered your question.
Amit is saying that he was talking about manufacturing industry.
Okay.
I guess.
Yes. Amit, again, it is very open-ended, but I assume that you're talking about a plant where something is manufactured and there are conveyor belts running, and something is moving throughout the whole industry. That is what I'm assuming that you're talking about. In such a case, one of the sensor that I can think about is proximity sensor. If something is moving from location A to B, you have to have multiple proximity sensors to detect where that particular uh, whatever is being manufactured is moving. So you have to detect where it is right now. Another sensor that I've seen very much commonly used in manufacturing industry nowadays is barcode sensors. What they do is anything that is being manufactured, they have a automated system wherein they stick a barcode or maybe a QR code also, and they have scanners placed at different locations just to decide where that particular manufactured part is supposed to be separated at. Uh, Also, one of the sensors that I've seen commonly used is temperature sensor, and these are temperature guns that they are using. These are industrial temperature sensors, which are being located at a place wherein they can verify or scan the temperature of that particular thing that is manufactured, and based on that, either they send the uh, output to the another conveyor belt which goes through the cooling system, or it goes directly to the station where it is being packed or something like that. So these are some of the examples that I can give right now.
Any more questions? Can take last 2-3 questions. If you have any questions related to problem statements or like some concepts that you want to implement or in the hackathon problem statement solution, you can ask. We have one question like how you build logic to write code for industry oriented projects.
Uh, Vinayak, it is not different from the the logic that you're going to use for either industry oriented project for or any other project. Even for your college projects, the logic still remains the same or supposed to remain the same. The way I talked about, you're supposed to plan first. See, uh, I think writing the code is the easiest part. You first decide what the logic is, and that is the most critical part. So, and it is not going to happen in one go. You will have to have multiple iterations that are supposed to happen, and then you reach a stage wherein you finalize what the logic is supposed to be. Uh, if you're talking particularly about industrial projects, one thing that is supposed to be taken care of is about the action that is supposed to be taken. So, uh, suppose you have a what industry project that we can take as an example. Suppose you are, uh, it is a very vague example. Suppose you are trying to build bricks that are being used for construction project. So the input is supposed to be a mixture of cement and all the other materials. Suppose example, you are building cement bricks, and it is automated industry wherein the input is raw material mixture of cement and other um, everything that is required to make a brick. And then there is a system in between in which it will be compressed, fixed together, maybe heated. And so there are going to be multiple stages that are going to be there. Pressurizing the raw material, it moves ahead. There is a temperature compartment wherein it will be heated, it moves ahead. Maybe there is a cooling system to suddenly cool it down so that it becomes rugged. And then there is a conveyor belt where it moves to the station where it is stored. So everything is automated. Now, since you know the flow of the system, since you know the events that are going to happen, you can easily define the logic that the raw material goes into the compressor chamber compartment for 1 second. The time is calculated based on how much it is required to fill in that compartment. Then the pressurizing takes suppose 2 minutes. So you stay there for 2 minutes. Then the conveyor belt is started so that it moves to the next session that is heating. There you heat it for suppose 30 seconds. Then it moves ahead. Again, you can have temperature sensor here so that you see that the temperature chamber is at the right temperature. If it is not, you have to wait for more time, or you have to turn on the heating element so that your temperature reaches that stage. and then you have a feedback mechanism, you have a temperature sensor to monitor that it has reached, and then you actually send the brick inside for 30 seconds. So since you know the flow of events, you can easily define the logic. So you are supposed to know what actually is supposed to be the output of the whole system, and then you define the flow.
Okay. Yes, we can end with this question if there are no any other questions.
Yes.
So okay. So I'd like to thank you, Bharat sir, for your wonderful session and valuable insights. And so we look forward to your mentoring for the selected teams uh, as we progress in this hackathon.
Yes. Thank you, Saurabh.
Yeah,
Thank you for inviting me.
our pleasure. And also the all thank you to all the participants who participated in this webinar and also in this hackathon. So I hope this session must have given you a new perspective and idea to improvise your solution that you are working for this hackathon, or even any other project that you are doing in your college or any other in your career. So again, we like to appeal you to participate in the hackathon if you haven't, and submit your solutions, innovative solutions before the deadline. And we look forward to have you in the grand finale as well. Of course, Bharat sir will be there as the one of the mentor and also as the evaluator. Thank you.
Okay. Thank you, Saurabh. Thank you, participants. Bye bye.
Yeah, thank you, sir.